Are you guys able to see the screen?
Yes, sir.
Okay. Let us quickly do the recap. In the last class, we talked about machine learning, correct? And in machine learning, we talked about the basic classification of machine learning, that is regression and classification. Are you guys with me?
Yes, sir.
One minute. We talked about the basic classification of machine learning, that is basically your supervised approach and unsupervised approach. Under supervised approach, we have regression and classification, whereas in unsupervised approach, we have clustering and dimensionality detection. Okay, so after this discussion, we moved on to the linear regression part, where we talked about the simplest form of regression, that is linear regression, correct? And we talked about having a relationship between the target variable y with the in the independent variable x. Basically your y is your dependent variable and x is your independent variable or explanatory variable, correct? So basically when you plot a simple scatter plot using the independent variable and the dependent variable on y-axis, you imagine a sort of a curve or a line at the center of these points, correct? And with this deduction, we came to the simple form of the equation for a linear regression, that is y equal to ax plus b, or with our example of ice cream sales, we call it as ice cream sales equal to a into temperature plus b. So once we deduce this equation, we moved on to talking about different hypotheses, such as having ice cream sales equal to 0.5 times temperature plus, what is the equation? It was 0 here. And we came up with another hypothesis where ice cream sales equal to 1.5 times the temperature plus 30. Are you guys with me?
Yes, sir.
And we deduce that with this hypothesis, in order to validate these hypotheses, we need to have a evaluation matrix, that is nothing but your aggregate error, correct? And whichever model gives you the lowest aggregate error, we choose that model. Okay, we will go on in detail during this session and understand, get more clarity over this topic. Correct? The quick question: is regression same as correlation? Is regression same as correlation? Any guesses?
No.
Okay, let's
It's not
say,
the same.
okay, let me explain. Let's say we have an explanatory variable x, okay, and a target variable y. Okay, we have the basic, we draw a plot, scatter plot of all the data points of x and y, and the plot will look something like this. Okay, and the regression, for all you know, is an imaginary line that passes in between these points. You're just imagining the line passing through the middle of all these points. Okay, now coming to the regression. Coming to the regression, coming to the correlation, let me give you some examples where you can tell me the R values. Okay, now you can call it as A, B, C, D. Okay, and in B we have something like this. In C I can have everywhere. D. Okay, now what is the R value for A? What is the correlation value for A? We all know that R varies between -1 to +1, correct? We studied this in EDA classes.
Yes, sir.
What
Minus
is the R
1
value
plus
for
1.
A?
Minus 1 plus
Yeah, R equal to -1 here.
minus, yeah.
Correct. And for C, I can say R is less than 0. Correct. We can't actually give you a value, but we see that there is this curve going downwards. Correct. Okay. And for D, any guesses? R equal to 0, right?
Yes, sir.
Okay. How about E? Now I see that there is a positive trend, correct?
Yes, sir.
So R is greater than
Greater than 0.
0. G?
Greater than, no, G is 1.
G is +1,
Yes.
correct? So we all remember this R value. It ranges between -1 to +1. Okay. So coming back to the question, is regression same as correlation? The answer is no. Okay. We have correlation and regression. Okay. So basically correlation is between any two variables, correct? We have only two variables here, one on the x-axis, one on the x-axis, one on the y-axis, correct?
Yes,
Whereas
sir.
hi Rahul.
Hi, sir.
And the value of the correlation coefficient will be in between -1 to +1. Okay. Whereas regression is hypothesizing a causation. Hypothesizing a causation. We are saying that y changes with x. Y changes with x. Hence, regression is not a particular value. Regression is actually an equation. Regression is actually an equation. Correct? Are you guys with me?
Yes, sir.
So regression is a way to map one variable with another. Correlation is just a number which shows how they are related. So in regression, you have y is the target variable and x's are your explanatory variables. Whereas in correlation, you have only two variable, that is, it's between variable. You see the relationship between your target variable and your explanatory variable here, whereas it is only between two variables. It could be both explanatory variable or it could be with respect to target or explanatory, but we just call it as between two variables here. Hence regression and correlation are not a little different, they are completely different. Is it clear?
Yes, sir.
Yes, sir.
I'll give you an example. Okay, let's look at this example. We have the size, that is square foot of the house. Okay, and we have the size of the hall, and we have the price, house price. Okay, now if I plot a scatter plot between the size of hall and the size of house, will they be related? Will they be correlated? Let's say the scatter plot comes something like this.
Slightly a correlation will be there.
I can say something like R equal to plus 0.8. So bigger the house, bigger is the hall. Correct? But is one causing the other? The answer is no. They just happen to be there. They just happen to be together. The person who's designing the house usually designs in the fashion where he take equal proportion between the size of the house, the square feet of the house, and the square feet of the hall. Correct? They're always correlated. So now let's talk about the price. Okay, is the size causing the house price? Can we hypothesize it? Yes, right?
Yes, sir.
We can hypothesize this, right? When you have the price and you take the size of house, whatever scatter plot you get, you don't just talk about correlation here, you talk about a hypothesis, a relationship. So this particular relationship is not a number, correct? It's a equation. Is it clear? Are you guys with me?
Yes, sir.
Shaina, Samantha, is it clear?
Yes, sir.
Yes, sir.
Now, let us do a quick activity on the correlation before we move forward. Okay. Now, let me call this as 1, 2, and 3. And let me have a chart A, chart B, and chart C. Okay. Chart A, I have the point something like this, whereas in B, the point something like this, and in C, have point something like this. Now, for point number 1, which chart suits the best for a correlation of minus 0.65?
Maybe B.
It's B. Okay. Coming to plus 0.8,
C.
it's C. And for correlation minus 0.81,
A.
A.
it is A. Okay. Now, let's now go directly to the regression. Okay. As we know, in linear regression, we need to find a relationship between one or more independent variables, okay, and one dependent variable or a target variable. So this is your target variable or dependent variable, whereas these are your independent or explanatory variable, correct? And we know that when you get a data set, you will have some kind of ID variable here, correct? 0, 1, 2, correct? Or 10, 11, 12, 13, something like this, correct?
Yes, sir.
Something like apartment number or a roll number, correct? So, but when you do the when we do the machine learning, we have to drop this or convert this to an index, however it is. Okay. To keep the discussion very simple, let us just stick to only one variable. Let us stick to the area in square feet, okay, and the house pricing. Let us only stick to this. One's explanatory variable and our target variable. We have, let's say, the area in square feet and my house price. Okay. For 3,500 square feet, it is 45 lakhs. 500 square feet, let's say it's 10 lakhs. 4,500 square feet, 50 lakhs. 1,000 square feet, we have 100 lakhs, and so on. Okay. So we had discussed this example before, right, in our previous class, similar to my ice cream sales. Whereas we only had temperature and my ice cream sales. You guys remember?
Yes, sir.
So we try to find the relationship between my temperature and my ice cream sales, correct? And we try to do a prediction. So the best way to do the prediction is to extend this table, put the ice cream sales predicted value here, correct? So based on the relationship what we find here, we try to do the predictions, extend the table and put it over there. Anyway, I lost it. And we came up with the equation, that is ice cream sales is equal to a constant into temperature plus another constant. You have seen this hypothesis, right?
Yes, sir.
Now, so this is from our earlier discussion. Okay. Now, who is stopping me to hypothesize something like this? Ice cream sales equal to A into temperature square plus B. Let's say ice cream sales equal to A into under root of temperature plus B. So instead of changing the values of A and B like we did in the last class, I am changing the way I am putting temperature in the equation. I can take square of temperature, I can take under root, I can take cube root, or I can also take ice cream sales equal to A to the power of temperature plus B. I can take a best example to this. As the days goes by, the number of corona cases goes up exponential. We all saw that equation in, I mean, the curve in the TV, right? The cases, how it went up, then it came down, then second wave came, went up and down, correct?
Yes, sir.
So the general hypothesis could be any of these. But to keep our discussion simple, we are considering this equation, the simplest form. So we are keeping the simplest form because it will help you to get clarity on linear regression and regression as a whole topic. Okay, now coming to the definition of linear regression. So linear regression is an approach. Okay, it is a linear approach. So linear is a straight line, that is the simplest form of approach, correct, to model the relationship between a response, a dependent variable. This could be only one variable. We call it as target variable, correct, and one or more explanatory variable or independent variable. Are you with me?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
That effectively means we will have to define what is a straight line. Okay, let us quickly talk about the straight line. Now ignore this, whatever you see on the screen, you just ignore. This is only for my reference. Okay, we all know that the equation of a straight line comes in something like mx plus c, correct, where m
Yes.
is your
Slope.
slope,
C is the intercept.
intercept. Okay, now let us not go in detail of how to find slope or how to find intercept. Okay, just for our understanding, let us simply define a line. Okay, I could say this as equation. The distance from my x-axis, this distance is nothing but my
Intercept.
intercept, and the angle it forms between the x-axis and the line is called as my
Slope.
slope, correct. Whatever may be the x value, we calculate y by multiplying it with slope and adding the intercept. I can give an example, something like y equal to 2x plus y. We all had this in our college, correct.
Yes, sir.
The reason why I'm bringing this topic here is, technically, when I said ice cream sales equal to A into temperature plus B, I am actually saying this as in this form, mx plus c, correct, where A is my slope and B is my intercept, correct. Are you guys with me?
Yes, sir.
Yes, sir. Yes, sir.
So we have been using this equation intuitively throughout our lives, correct. So let us not go in detail and understand how to find out slope and all that, because you will not going to use it anywhere. Okay, so So the challenge what we have is to find the right value of all these equations. You can take care. So the challenge what we have is to find the right value of my coefficient okay. So the challenge lies in finding the right value of coefficient and bias, but we don't call it as bias because in machine learning bias has a different term. Okay, let's call it as intercept. Let us not use the word bias because as and when you learn machine learning, as and when you go in detail, bias has a totally different meaning. Okay, such that we have least error. Okay, so the objective now is, if we have a data set of ice cream sales and the temperature, if you have this data set, the real objective is what is the value of A and B such that my equation, okay, such that my equation has a right fit. Okay, so if we are able to find these values, we will be able to find the relationship to predict the ice cream sales. So I would know what is the number of ice creams I should keep in my shop to have the right amount of the sales. So I can predict my future of, the ice cream sales in the future depending upon the forecast of temperature. So the question is, we need to know the right value of A and B. So before we get there, let us go on to a scatter plot. Before we get there, let us quickly discuss about the scatter plot. I have my ice cream sales here and I have my temperature on the x-axis. Okay, and you said that it is an actual equation of a line with the equation ice cream sales equal to A into temperature plus B. So if this is correct, then it can be plotted, correct? If this is correct, I can plot this. So let us quickly plot it. Okay. Can I plot the line in this manner?
No, sir. It should be in such a way that like it is in between those. It passes through the points.
It should pass through the point. Let me use the color blue. You mean to say it should pass through the point.
Yes.
Okay, let me call this as 1. Let me call this as 2. Okay. How about this line? Again, no, correct? This line,
The slope might be correct, but not the intercept.
still there is
Okay.
a gap. Yes.
Yeah.
Okay. So no matter where I place my green line, okay, you would say blue is the best fit. Blue looks better. Why? Why is that? What is special about blue line?
Because it has the right slope and the right intercept, something like that.
Like best fit line, it is having the right
Yeah,
slopes.
it has least errors.
It has least error. Yes. Correct. It has
Minimum deviation with it.
minimum error. I can say it has best fit. So our objective was to find A and B such that overall error is minimum. Okay. So for all the other plots, what we discussed here, all the other charts, these could be the different hypotheses. The error is not minimum, but for the blue line, we have the least error. Are you with me?
Yes, sir.
But if we hypothesize this and this turns out to be true, okay, if this turns out to be true, then we need to find this overall error, or we need to define this aggregate error, correct? Once we define this aggregate error, then we can minimize it, correct? Once we are able to find aggregate error, if we are able to minimize it error, then we will know the right value of A and B. Agree with me? Let's say for different values of A and B, okay, we have different aggregate error. Okay, so whichever has the least amount of error, we have the most suitable for of A and B, and this will give you a best fit line. Are you guys with me? Once you have this best fit, this line will pass through the center, or it will pass through the middle. But for this discussion to be possible, we need to define the aggregate error. We need to define this mathematically. Basically, how do I sum up? Should I go? Let's say, let me take temperature. Okay, I have my actual ice cream sales. Okay, I have my predicted ice cream sales. Okay, I have my error E. Okay. So to understand the error, to understand my prediction, basically I need to define, how do I define the error? Should I aggregate it? Should I take the mean? Should I take the mode and the sum? I need to define it mathematically. Okay. Let's say for different values of temperature, I have the sales as 9, 12, and so on. And my predicted would be, let's say I predicted 10, 2, 8, 13, 6, and so on. And I will define error as my actual minus predicted. Okay. So actual would be 5. So 5 minus 10
-5.
minus 5. 6 minus 2, 4.
4.
5 minus 8, minus 3. 9 minus 13,
-4.
12 minus
6.
6, 6. Okay. Now, so let me tell you the aggregate error defined in linear regression. In linear regression, we define the aggregate error in terms of RMSE. Have you guys heard about this before? Anybody?
Minimum squared something.
No problem. It is root mean
Root means square equation.
error.
Root means square error.
Okay. Basically, what you do is you define it backwards. I have my error. Okay. I have to square it. I have to square it. I have to take mean of it, and then I have to take square root of it. Are you guys with me?
Yes, sir.
To understand the RMSE in detail, we need to understand linear regression as a whole first. Okay. Only then we can spend about 15 to 20 minutes on root mean square error and other type of error in model evaluation technique. Okay. But in order to give you clarity on RMSE and this formula, let me take you to Excel. Let me take you to Excel. Okay. Let me delete it. This Excel is already uploaded in your LMS portal. I just uploaded this morning. Okay. So basically, I have my height and the weight. I have about 200 rows of data of my height and the weight. Okay. If I plot it, I get my chart something like this. I get my chart something like this. And put the chart here. Okay. This is the basic representation of my data set. For different values of height, I have my weight. So basically, I have to predict what is the weight of a person given the height. Is this clear?
Yes, sir.
Now, is the weight dependent on the height? In general, can I say that the taller the person, more heavier would he would be?
Yes, sir.
Okay. You can also see it in the scatter plot, right? There is a relationship. Okay. Now, you can see this line, correct? You can see this, correct? This relationship. I can say that the weight of the person depends on the height, or the height of the person depends on the weight. Are you guys with me?
Yes, sir.
Okay. Now let's carry out the linear regression here. Let me quickly give this as actual. I will give predicted here. Okay. And let me give different color. Now I would define slope and intercept. Okay. Now let us consider the slope as 1 and intercept as 10. Okay. And the equation would be equal to slope would be my m, correct? And the intercept would be my c. Okay. And the equation is y equal to m into my height plus c. This is my target variable. So equal to m function f4, because I have to freeze itself, into plus c function f4. Okay. I have my prediction. Okay. Now let me draw it. Let me put it on a scatter plot. Let me put it on a scatter plot. Is it clear to you guys?
Yes, sir.
China, Samantha?
Yes, sir.
Okay. Now, as and when I'm varying my slope and my intercept, I'll know my different hypothesis. I am trying different hypotheses, and based on that, I am understanding the different fits. Correct? So we started with the random number of slope and hypothesis. Now, is this a straight line? Is this a straight line?
Yes, sir.
Correct, it's a straight line. But is it a best fit? Does the fit looks good?
Yeah, it is somewhat looking parallel. No, but the intercept is not.
It's not a good fit, no? It's
Yeah.
quite far. Your intercept is big. So let me reduce the
Yeah.
intercept. Let me reduce it to, let's say, 5. Still no effect. Let me reduce it to 1. Still no. Let's go to 0.5. Still no. Okay. Let me try reducing the slope. Let me commit to 1. Okay. Now it's lower. Let me increase the intercept to 2. Still no. Let me increase it to 10. Still no. Correct. But this trial and error will continue forever. Correct. Are you guys with me?
Yes, sir.
Yes, sir.
But you can see that by changing the slope and intercept, we are effectively changing the line. So in Excel, we have a good thing called as a solver. Okay. There's a good thing called as a solver, which can do this number of iterations. Okay. And give me the best fit line. But in order to do it, I need to define the theory for minimizing. What should I effectively minimize? Basically, we set an objective to minimize my error, correct? So let us define my error. Error is nothing but my actual minus predicted. Actual minus predicted. Correct? Are you guys with me?
Yes, sir.
Okay. But this is only an error. I need my aggregate error. That is nothing but RMSE. So to get the aggregate error, I need to know sum square of my error. Okay. Divided by my the total, and I need to take a under root of the whole thing. Clear? Are you guys with me? I have my error. I have to square my error. Correct? I have squared my sum. I have taken the sum, I have squared it. Okay. And I have to take a mean of it. So I divided by the total to get the mean, and I have to take the under root. Are you guys with me?
Yes, sir.
Okay. In Excel, when you go to file, no, in options, you have add-ins. Under add-in, if you click here, under Excel add-in, click on go, you have solver. If somebody is in front of the system and you are using Excel, you can just add it. Okay. Once that is done, you can go to data. You have your solver here. So set the objective. What is our objective? Is to minimize my error. I have to minimize this. What do I have to do? I have to minimize my objective. By changing the variables, what should I change? I need to take trials on these two variables. I have to keep changing this so that my error gets minimum. Are there any constraints? No. make unconstrained variables non-negative. I am okay to take the answer in negative as well. I'll click on this and I give solve. And I give OK. Voila. I have my best fit line. I have my RMSE as lowest possible. My slope is here. My intercept is here. Are you guys with me?
Yes, sir.
You guys might doubt that my intercept is on negative side, whereas here it's showing positive side. That is because the scale starts from 62. Instead of that, if I start with 0, you will understand that it actually goes on the negative side. Is this clear?
Yes, sir.
Any doubts? Now, is this the optimum solution? Is this the optimum solution? Is this the optimum solution? The answer is yes. It is the optimum solution. I still see that there are some errors here. Correct? There are some errors here. Now these errors are called irreducible errors. The reason why they are called irreducible error because we cannot reduce these errors any further. The irreducible error will occur in this scenario is for the fact that for any given height, the weight of the person could be more or less. The person may be fat, the person may be thin. It can vary from this to this. Correct? People do not follow the normal line. Now with that, we have that equation ready. Okay. Can I ask you to predict the weight of a given height to exact value?
Yes, sir.
To the exact value.
No, these are predicted, right? So the answer we get also will be predicted.
You can only go to some decent value, right? You can only go to that
Yes.
decent value. some decent value you can predict. They'll always have some error. You cannot fine tune it any further. So hope with this you are able to understand the basic gist of the linear regression. So now you have worked on the objective to find A and B such that my aggregate error is minimum. Are you guys with me?
Yes, sir.
Okay. Any doubts? Samantha, Shaina, any doubts?
No, sir.
Okay. Let us quickly take a small break and then we'll resume at 12:30.
Okay, sir.
Okay, sir.
Yes, sir.
Is everyone back?
Yes, sir.
Yes, sir.
Shaina, are you back? Shaina, are you back? Shaina, are you back?
Yes, sir.
Okay. So basically, we talked about our basic hypothesis of finding A's and B's such that our aggregate error is minimum. Then we went on defining what is the aggregate error and understood what exactly is RMSE, and we completed our Excel activity. So in the world of machine learning, we don't call them by A or B or M or C. Normally, we give the abbreviation as y equal to beta 0 plus beta 1x. Whereas your betas, this beta 0, beta 1 are called coefficients. These are termed as coefficients. So the reason why we are doing this is because tomorrow, let's say we have multiple variables, we have more variables, then we can go on representing something like this: beta 0, beta 1 x1, beta 2 x2, and so on. So if we go with ABC notation, we'll end up missing the alphabets. Are you guys with me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, our motto throughout the discussion was not to get a line of perfect fit, but to get the line which was best fit with the least amount of error. Hope everyone is very clear on what we discussed today. Okay. Now that you have seen all this, let us see how good or bad algorithm is. Okay. Unless or until you use this algorithm for predicting, you won't be able to know how good or bad the algorithm is. Correct? Let's say you have multiple models for tomorrow. Okay. Let's say the CEO of housing.com website will ask you to make a model to predict the house prices. So while you're working on the model, you come up with a lot of assumptions such as price depends on the square feet, price depends on the distance from market, price depends on distance from let's say metro station, your price depends on distance from market plus your square feet. Okay, you come up with different hypotheses and you make multiple models. Okay, and for each of these model you find the RMSE value. Whichever the model has the lowest RMSE, you will choose that model as the best fit model. Are you guys with me?
Yes, sir.
Okay. That is how you are comparing your different hypothesis with respect to your aggregate error with respect to each hypothesis to come up with the best fit line. Okay, now before we get to the model evaluation, okay, what are we why are we constructing the model?
To check whether what analysis you have done, whether there are any errors in that.
To predict, correct?
Yes, sir.
You construct the model to predict. So predict when? Predict when? Or predict on what data? Do you use historical data to predict?
We look at the data given and then
Correct.
we predict.
Historical data can be used to learn how to predict, but prediction is always on tomorrow's data, right?
Yes.
The prediction, what you're going to do is always on tomorrow's data. You use your historical data to build the model and you do the prediction on tomorrow's data. Okay. You have your historical data. Okay. With this, you make a model to find your betas, the coefficients. Okay. Once you have the coefficients, you have your beta 0, beta 1, beta 2, correct? And from tomorrow's data, you have your x's. With the combination of both, you can do prediction. Are you guys with me?
Yes, sir.
Okay. Now, if you understand this, shouldn't be checking of the algorithm if it works or not happen for tomorrow's data? Correct? You constructed the model with the historical data, you got your betas, okay? You have the model ready. Let's say y equal to beta naught plus beta 1x. This is your model, okay? If you have to check this model, whether it will work perfectly or not, don't you think you need to use tomorrow's data to do it? For your validation? How can you check on yesterday's data? You already used it, right? For your model building. How will I know that whatever data I used to build the model and to get the trend, how will I know if tomorrow's data will follow the same trend or not?
We have to apply the same and check.
Yes, we can apply the same and check, but do I have to wait till tomorrow to get that one data point? Let's say I have the data of whole year of 2021, and to do the tomorrow's prediction, I only get one data point.
We can just see the previous values and predict.
What you can do is, okay, I can pass on. Let's say I have my data set. Okay, I make a model. I find RMSE of this data set. Okay, now I have to pass on unseen data to model and get the RMSE and check if agrees with the trend. Is it clear? I need to have unseen data with my Y, correct? So that I can do the prediction, compare it, take out RMSE and see if it justifies. So the basic trend what is followed here is, let's say this is your original data set. Okay, what I do is I take up 80% of my data. Randomly, I take out 80% of my data and I call it as train set. Okay, and the balance 20% of my random data is called my test data or the test set. Okay, now this data is basically my proxy for tomorrow. Okay, whatever train data I have, I construct my model. I create my model with respect to my train data. Okay, once my model is done and I get low error, in order to check if the model behaves perfectly for unseen data, I feed this into the model. Okay, and then I check model behavior. If it justifies, then I can say my algorithm is good. Are you with me? Samantha, is it clear?
Yes, sir.
Basically, my original data, before I start the model building process, I split it into train and test. I use 80% of my random data, let's say 80 or 70, whatever it is, and I train my model. Once the model is ready, I pull out that 20% of the data which was hidden earlier. This was totally hidden to my model before. I pull this data, feed it to the model, and check how it behaves. If it justifies, if the model predicts in the right manner as it did for the trained data, then the algorithm is good. Else we have to go back and do our check our assumptions or check our hypothesis. Now this process will happen not just for linear regression, this process will happen for every algorithm in Python. For every algorithm, we have to do this process. And this process is called as train test split. Okay, in theory or books, this process is called as cross cross validation. Are you guys with me?
Yes,
Yes.
sir.
Any doubts? Now, with this concept, let us describe quickly two things. Can we measure the accuracy of the model? Let us do one thing. Let us go back to our Excel. Let us go back to our Excel and do this activity. You guys are able to see the screen, right?
Yes, sir.
Okay. Now, I will use there are 200 rows of data. Okay. How much will be 20%? That is 40 rows, correct? Let's say I'll use 60 rows or 50 rows. Okay. I'll take out this 50 rows of data and I put it here. Now, I call this as data set. Okay. And this is where I will do my training, model training. Okay. Now this data set, what I have in test is totally hidden from my model creation technique. I did my cross validation now. Now with this, let us quickly define slope. Okay. And my intercept. Okay. I'll give just random numbers and I will do my weight predicted. We'll give this color. Now here, tell me the equation. Equal to
Slope into
slope. Let me freeze it out into
height
height plus
intercept.
intercept. Freeze the cell.
So instead of plus, it is instead of equal to, it is plus.
Okay. Now, let me define error. Error is nothing but
Actual minus predicted.
actual minus predicted. Okay. Let me define RMSE. RMSE equal to my error, that is sum square of these values divided by count of these values. Okay, and I take a square root of everything. Okay, now let's quickly plot it. Mhm. Correct. Okay, now what is the next step? What is the next step? Shaina, what is the next step? I have to optimize my model, right?
Yes, sir. Find the adjust the slope and intercept.
Correct. I use solver.
Yes, sir. Solve.
Okay, so objective is this. By changing the value, these two, I have to minimize my objective. I don't have any constraints, and I'm okay with accepting negative values here. Solve, and I get my RMS as 9.7. Correct. Okay, now what will be my equation? What is M? 3.43
3.43.
plus.
So 3.43 into x
Yeah, into x. It will be
minus
minus 105.87.
87.
Now I'll just take this here. That means I have to copy my slope and intercept here. Okay, I copy my slope and intercept, and I take my y predicted of my test data. Correct. That is equal to into my x plus intercept. Okay, and I found file, and I'll find my error, that is actual minus predicted. And let me copy paste my Cindy only, right? Cindy only. RMSC. Is up to 27. Okay. Is the error minimum? In the train data, I had an error of 10.79. In the test data, I have an error of 10.69. I mean, train data we had 9.79. Test data I have 10.69. Can you justify this error?
Because the independent variables or the height values changed.
That is totally fine, right? I can justify this error. This is very close. I cannot accept the error to be exactly the same. But I can say that the model is behaving perfectly.
Yes, sir.
Even for tomorrow's data, which was unseen over here in my model, that is perfectly behaving, correct?
Yes, sir.
Correct? Are you guys with me?
Yes, sir.
So basically, this data is the proxy of what's going to happen tomorrow. I will not have this value at all. I will only have my input and I should predict what is output, what is going to happen. Okay. So in order to do that, I will split my historical data into train test 70-30 or 80-20. Based on that 70% of the data I will use for my model building. Once the model is built with the least amount of error or the best fit line, I use this model here to do my prediction. So test data is basically a better version of data to check what is going to happen tomorrow. Will the prediction be right? If it goes on the if it makes a lot of error, then what could be the maximum error it could happen? See, the variation with respect to 9.79 to 10.69 was hardly close to a single 1 point of RMSE. It's still on the lower side. The model which can have an abnormal behavior is the one where you have a train of 10 and a test data giving RMSE as 100. That gap will be too much, right? If I have to discuss in terms of percentage, let's say your test data gave an accuracy of 96% and your train data gives an accuracy of 92%, then it's still a good model. If the model is not good, let's say your train data gave an accuracy of 96 and the test data gave an accuracy of 95, then something is wrong with the model. Are you with me?
Yes, sir.
Okay. Now the question what would arise is how much data? Okay. What would be the minimum number of data points you need for prediction to carry out this testing? Okay. What would be the minimum number of data points we need to use to carry out the testing? So what you can do is you can use a thumb rule of 10x square. Okay. You can use a thumb rule of 10x square where x is the number of explanatory variables. There are other thumb rules like your 4x square. Let me just note it down over here. This is the minimum number of 10 data point, that is 10x square, where x is your number of explanatory variables. In our case, what we did, Excel activity, x is 1. So you need to have minimum 10 points to do this exercise. Whereas here we used 25 points. Okay. There are other thumb rules such as 4x square or just 10x or 20x. Okay. You can follow any of these. Are you guys with me?
Yes.
Any doubts? So this is where I stop my session here for today. In the next class, we can discuss on the another metrics that is used to evaluate a model, that is R square. Okay, and then probably in the next class we will have some Python activity where we'll actually do or carry out a linear regression on a data set. Okay. Yes, Rahul.
So while testing this, you told right now if the test data was 96% accurate and it is 92. So 96, 92, we accept it. So till how long we can keep on accepting it? Like, is there a certain limit which is given?
There is no particular limit as such. Basically, when you learn machine learning, okay, as and when you proceed with the topics, you will understand that sometimes when you do your testing and training and testing, okay, sometimes the model gives an accuracy of 100% for your trained data. Okay, that is when you understand that your model is overfitted. Okay, and there is another topic where your trained data gives some accuracy of hardly 50%. This is where you understand that the model is underfitted. Okay, so your question on what should be the acceptable range for your model with respect to train and test will be very clear to you when you understand overfitting and underfitting of models. Okay, for that,
Yes.
you need to learn at least 2 models in linear regression, or minimum 2 models you need to learn so that you can compare between 2 models. For now, in supervised learning under regression, we just started linear regression. We have not even touched your decision trees, your random forest, or support vector, any of the other algorithms. We are only working with first model. So as and when you proceed and understand what is overfitting, what is underfitting, then these things will be very clear to you.
Understood.
So basically, there is no thumb rule of how much is acceptable, how much is not acceptable, because there will be some complicated data sets which hardly gives you like 60% of your accuracy and still have to implement it. Any other doubts?
Yes, sir, because sometimes there will be sudden jumps in the independent values also. So it might affect the data, right?
Yeah, when you have
Like
outliers in your data, definitely it will affect.
in the previous, the example which we took, the heights were around 60, 70, the values. So it was in that range. So we got some 92% accuracy, 60 to 71 range. So if it varied in the train data, then the error also might increase, right?
Correct. Basically, in your regression, we don't call it as an accuracy. We normally measure the performance of regression through RMSE, you have MSE, that is mean squared error. You have basically we use just a mean, or we use R squared error. Okay, we don't call the word accuracy. Accuracy comes in your classification.
Okay, sir.
It basically comes in your classification models, but we can talk about model accuracy with respect to the RMSE value in regression. Since in regression, the problem is that RMSE is just a number, correct? It's just a number.
Yes, sir.
The only way to make out whether RMSE is a good number or a bad number, to have multiple regression models and to see the respective RMSE values. Whichever is lowest one, you select it. Okay. Whereas in classification, you get accuracy in terms of percentage. On the scale of 1 to 100%, how good the model is, you can gauge the model with respect to the percentage. So the difference is that accuracy with classification should be as high as possible, whereas in regression, the RMSE should be as low as possible. Is it clear?
Yes, sir.
Why Shaina and Samantha are very silent? No doubts from them.
Not very well, sir. That's why.
Samantha, any doubts?
No, sir.
Okay. You can drop off today in case you don't have any doubts. And we'll continue our discussion on regression in next class.
Thank you, sir.
Thank you.
Thank you, sir. Have a
Thank
great
you,
day.
sir.
Thank you.